Okay, let's go back to section 1.7 a minute. In section 1.7, we defined a non-singular matrix, square matrices. Okay, we're only talking about square matrices now, and in section 1.9 inverses, we're strictly talking about square matrices. So for the rest of this video, A is always a square matrix. But so remember that the definition of a non-singular matrix was that AX equals 0 has only the solution X equals 0. That is, the columns are independent. Therefore, A times coefficient vector equals the 0 has only the solution where all the coefficients are 0. So that means that if A is non-singular, that is, the columns are independent, the square matrix, remember, then when you reduce it down to reduced echelon form, you don't end up with any rows of 0, because otherwise if you ended up with one or more rows of zeros, there would be many solutions, because there would be at least one arbitrary constant, one arbitrary x. So if the columns are independent, AX equals 0 has only the solution X equals 0. It's the definition of columns being independent. That means that if you reduce A down to echelon form, you do not end up with a row of zeros. You end up with the identity matrix, all ones and zeros. And then the only solution is X equals 0. Well, this theorem here says that if A is non-singular, AX equals B has a unique solution for any B, and that's evident because if you reduce a non-singular matrix down to row echelon form, it's not going to have any rows of zeros. Remember, we're talking about square matrices. It will not have any rows of 0, and therefore the solution, the reduced form will just be the identity, and therefore you just read off the solution on the right. So that's a non-singular matrix. On the other hand, if it's singular, not non-singular, that means you reduce it down and you have at least one row of zeros, and then you either have many solutions or no solutions, depending on whether the right-hand side has non-zeros in the last, the elements corresponding to the 0 rows. So basically, square matrices, there's good matrices and there's bad matrices. The good matrices, those are the non-singular ones, they have independent columns. AX equals 0 has only the solution X equals 0. AX equals B has a unique solution. The bad matrices, they're singular, the columns are not independent, they're dependent. Then AX equals 0 has many solutions, and AX equals B either has many solutions or no solutions. Okay, now to section 1.9. This is talking about inverses of a square matrix. Again, only square matrices can be invertible or non-invertible, and only square matrices can be singular or non-singular. But most matrices we're interested in solving real systems are square, because you usually have the same number of equations as unknowns. So usually the matrices we're interested in are square. So an invertible matrix is one who has an inverse. That means there's a matrix B such that AB is equal to the identity. So you're trying to find a matrix B such that A times B is the identity. Now, how would you go about finding that? Well, if B1, B2, and so forth are the columns of B, and E1, E2, and so forth are the columns of the identity matrix. In other words, E1 is 1, 0, 0, 0, 0, E2 is 0, 1, 0, 0, etc. En is 0, 0, 0, and the last element's 1. So basically, A times the first column of B is equal to the first column of I. A times the second column of B is equal to the second column of I, and so forth. So to find the inverse, you basically need to solve n different systems with the same matrix at different right-hand sides. Well, we just got through saying that if A is non-singular, AX equals B is going to have a unique solution. So no matter what the right-hand side is, you're going to have a unique solution if A is non-singular. So if A is non-singular, it will have an inverse, and you can find the inverse by solving these n linear systems simultaneously. And you can do that by as follows. So let's say we want to find the inverse of this 3 by 3 matrix here, if it has one, then basically you have to solve A times first column of inverse equals this, A times the second column inverse equals that, A times the third column of the inverse equals that. So basically you need to solve 3 linear systems with the same matrix, 3 different right-hand sides. So you reduce this down to, reduce the first 3 columns, the A, so you put the A here and the identity here, reduce this down by row operations to the identity matrix like that, and basically you're solving 3 systems but same matrix, so the same operations are done to A, just you do all 3 of them simultaneously here, parallel processing sort of. So every time you switch 2 rows, you switch it all the way across all 3 right-hand sides. Every time you take a multiple of one row and add it to the other, you do it all the way across and so forth. So after number of manipulations, you reduce this A down to the identity, and what's left here is exactly the inverse, because this is the solution to A times first column of the inverse equals first column of the identity and so forth. So you start with A and the identity here, and you reduce it down until the first 3 columns are the identity, and what's left will be the inverse. And that's assuming, of course, that you don't end up with any row of zeros here. If you do, then it doesn't have an inverse, because there'll either be many solutions or no solutions to each system here. So if it's invertible and if it's non-singular, you will not have a row of zeros. We just AX equals, AB equals identity column will have a unique solution for each column of the identity, because if A is non-singular, it'll reduce down to the identity. So that's how you find the inverse. Put the identity, the matrix here, the identity here, reduce A down to the identity, and what's here is the inverse. And that's assuming A is non-singular. So if A is non-singular, that is the columns are independent. The good matrices, it'll have an inverse. The bad matrices end up with a row of zeros and they don't have an inverse. And AX equals B does not have a unique solution for any B. That's why it's a bad matrix. So finding the inverse of a matrix is a fair amount of work, but if A is a 2 by 2 matrix, you can do it a lot simpler with a little something called Cramer's rule. Basically, Cramer's rule says if A is A, B, C, D, then the inverse, you switch the A and D and you change B and C, the sign, multiply B and C, the off-diagonal ones, by -1, but don't switch them. A and D, you switch them, and divide by the determinant, which is AD minus BC, and that will be the inverse, and that saves you from reducing this down to the identity, saves you some work. And you can verify just by directly multiplying this times that, and you'll see that you do get the identity. Well, assuming, of course, that this determinant is not 0. If the determinant is 0, that means the matrix is singular and doesn't have an inverse. Assuming the determinant is non-zero, that's the inverse, and you can just multiply them out and you see that you get the identity. So that's Cramer's rule is a nice little trick for 2 by 2 matrices you might want to remember. There is a Cramer's rule for larger matrices, but it's not very useful. Okay, what's an inverse good for? Well, if you're trying to solve a square linear system, again, A is assumed to be square in this whole section, and section 1.7 also. If A has an inverse, then you can just multiply both sides by A inverse, and A inverse A is the identity, so X is just A inverse B. So if A has an inverse, you can just multiply both sides, multiply B by A inverse, and that's your solution. Of course, that doesn't save you a whole lot of work if you're just solving one system, because it takes more work to find the inverse than it does to solve the system. But remember that AX equals B will have a unique solution if and only if A is non-singular, which means it has an inverse. If it doesn't have an inverse, then you can't do this, and AX equals B will either have no solution or many solutions. Theorem 17 has some properties of inverses. The inverse of an inverse is the original matrix. That's pretty easy to show. Just take that times A inverse and you get identity. Here's the interesting one, that AB inverse, assuming A and B have inverses, they're square matrices, so AB is square also. AB inverse is B inverse A inverse. In other words, the inverse of a product is a product of the inverses in reverse order. That's kind of like the transpose of a product is a product transposes in reverse order. This one's pretty easy to show that the inverse of AB is B inverse A inverse, and it's not A inverse B inverse. It has to be in the reverse order. Just multiply AB times what we're claiming that this is the inverse of AB, so multiply it by AB, and the B's cancel and the A's cancel, and you get the identity. So that proves, but it has to be in that order. So the inverse of AB is not A inverse B inverse, it's B inverse A inverse, which is generally not the same thing. Okay, the homework problems, you're supposed to find some inverses of a 2 by 2 and a 3 by 3. This problem, you're supposed to find the inverse of AC. Well, that's going to be C inverse A inverse, and it's given that C inverse is this and A inverse is that, so you just take this times that in that order. Alternative, you could find the inverse of A and inverse of C, and then you'd know A and C, then you could multiply that out and then take the inverse of that, but that involves finding 3 inverses. You have to invert this, multiply, invert that. Since you're actually given the inverses of A and C rather than A and C, so you just say, well, save a lot of work by saying that it's C inverse A inverse, so just multiply the two matrices. In fact, this theorem says that if A and B have inverses, so we're assuming A and B are invertible, that is non-singular, then AB has an inverse and it is B inverse A inverse. So if A and B are invertible, then the product is invertible. Now, one of the homework problems shows that that's not true of the sum of two matrices. So if A and B are non-singular, the A and B have inverses, then it's not necessarily true that A plus B has an inverse. To give an example, and it's pretty easy to come up with, such that A and B both have inverses, but A plus B does not. And then conversely, you can find matrices A and B that don't have inverses, and the sum does have an inverse, is non-singular.